A refrigerator does not manufacture cold. During operation, it removes heat from an already cold compartment and forces that heat into a warmer kitchen. Its back or side walls therefore become warm. The heat released to the room is also greater than the heat removed from the food, because the electrical work supplied to the compressor ultimately becomes heat as well. This sounds as though heat is moving against its natural direction. It can do so only because the refrigerator pays for that transfer with mechanical work. But the heat pump is only half the story. Humid room air enters whenever the door opens and can freeze on the evaporator, gradually blocking airflow and covering the heat exchanger with an insulating layer. To keep food cold, the refrigerator sometimes has to heat the coldest component in the machine. The cabinet surrounds an insulated box, door gaskets, and internal air passages. In many frost-free refrigerators, the evaporator and its fan are hidden behind an interior panel. Compartment air passes across the evaporator, loses heat, and is distributed back through the freezer and fresh food sections. The sealed refrigerant circuit has 4 essential regions. The compressor draws in low-pressure refrigerant vapor and compresses it to a higher pressure. The condenser, located outside the refrigerated space, receives that hot vapor and rejects heat to the room as the refrigerant condenses into liquid. A filter dryer retains moisture and contaminants. A long, narrow capillary tube restricts flow from the high-pressure side to the low-pressure evaporator. In the evaporator, refrigerant absorbs heat and returns to vapor before reaching the compressor again. No component sprays coldness onto the food. Refrigerant moves through the tubing. Heat moves across the tube walls. The fan carries compartment air over the heat exchange surface and distributes it where cooling is required. The freezer and fresh food compartment often share this cooling source. Air passages and dampers divide the available airflow, while sensors tell the controller how each region responds. Cooling the evaporator is therefore not enough. The system must also route that cooling without freezing food in one zone or leaving another too warm. The first physical enemy is the pressure difference. For refrigerant to evaporate below the compartment air temperature, the evaporator must remain at low pressure. For refrigerant to condense and release heat into the kitchen, the condenser must operate at a pressure that gives it a temperature above the room. The compressor must continually maintain these 2 regions. The second enemy is moisture. When room air enters, water vapor encounters evaporator surfaces below freezing and becomes frost. Even a thin layer reduces heat transfer. A thicker layer obstructs airflow. Running the compressor longer does not solve the cause, because a colder evaporator may continue accumulating ice. Heat also leaks through insulation and gaskets, and warm food adds a changing load. Each door opening changes the conditions. Air temperature may recover quickly while a large object remains warm internally. How can the appliance maintain different compartment temperatures, prevent the evaporator from becoming sealed in ice, and avoid wasting electricity by running continuously? The capillary tube adds another limitation. It is a fixed restriction rather than a valve that continuously chooses the perfect flow for every condition. Engineers match its diameter and length to the compressor and expected operating range. Changes in room temperature, food load, and pressure therefore shift the operating point of the entire sealed circuit. The core solution is to create 2 pressure levels within one closed circuit. The compressor receives low-pressure vapor and performs work on it. Pressure and temperature rise, making the discharge vapor hotter than room air. In the condenser, it can transfer heat outward and change into liquid while remaining at high pressure. The capillary tube is not an actively controlled spray nozzle. Its small diameter and length create flow resistance and limit the refrigerant entering the low-pressure side. As the liquid passes through the restriction, its pressure falls sharply. Part of it flashes into vapor, cooling the mixture. In the evaporator, the remaining liquid continues boiling by absorbing heat from compartment air. The compressor removes vapor from the evaporator, preventing pressure there from rising enough to undermine low-temperature boiling. At the same time, it pushes refrigerant toward the condenser and maintains the high-pressure side. Compressor work is what allows heat to be collected at a low temperature and rejected at a higher one. Phase change makes the heat exchangers effective. In the evaporator, refrigerant can absorb substantial energy while boiling through a limited temperature range. In the condenser, vapor releases energy as it becomes liquid. The coils provide area and airflow for these exchanges. The refrigerant does not merely become cold in one tube and hot in another without moving energy across their walls. To manage frost, a frost-free refrigerator periodically suspends normal cooling and delivers heat to the evaporator area with a defrost heater. Ice melts into water, flows through a trough and drain tube, and reaches a pan outside the refrigerated compartment. Heat near the compressor and condenser can help that water evaporate. The controller and temperature protection limit the event so the heat exchanger is cleared without warming the food compartments excessively. Defrost is itself an optimization problem. Performing it too rarely allows ice to restrict airflow and insulate the coil. Performing it too often adds heat that the refrigeration cycle must later remove. Timers, temperature sensing, accumulated compressor operation, or adaptive control can be used in different products to schedule the event. When cooling is requested, the compressor begins drawing vapor from the evaporator. Hot, high-pressure refrigerant travels to the condenser and returns to the kitchen, both the heat removed from inside and the compressor's electrical work. The liquid passes through the filter dreher, is metered by the capillary tube, and drops in pressure. It absorbs compartment heat and vaporizes in the evaporator. The fan moves air across the coil and distributes cooled air between compartments through the designed passages and dampers. Insulation slows heat entering the cabinet. Door gaskets reduce humid air exchange. The controller stops or reduces compressor output once temperature requirements are met. Frost nevertheless accumulates over time. When defrost conditions are reached, compressor cooling pauses. The heater melts the ice. Water leaves the coil, and a later refrigeration cycle restarts with an open heat transfer surface. Every subsystem solves part of the same problem. The refrigerant circuit moves heat. Insulation reduces the load. Airflow distributes cooling. Defrost restores heat transfer performance. The controller decides when to use each subsystem so refrigeration does not become continuous, uncontrolled electrical consumption. Closing the door does not instantly return the food to its target temperature. The sensor measures conditions at specific locations, while thermal mass responds over a longer period. Control logic must avoid reacting to every short fluctuation with excessive cycling, yet still respond to a sustained load, such as warm groceries or a leaking gasket. This is also why blocking an internal vent can create two opposite symptoms at once. One region receives too little cold air while another becomes colder than intended. The sealed circuit may still be operating correctly, but its useful heat transfer path has been interrupted after the evaporator. Refrigeration performance, therefore, depends on both the refrigerant loop and the air loop remaining open. A refrigerator remains cold by continually transporting heat outward. The compressor creates the pressure difference. The condenser rejects heat. The capillary tube reduces pressure, and the evaporator absorbs heat as refrigerant changes phase. Fans and insulation manage compartment air, while the defrost cycle removes the consequences of incoming moisture. Warm exterior surfaces and temporary pauses in cooling are not contradictions. They are evidence of a system that pumps heat against its natural direction, while protecting its own heat transfer path.